To ICANX Talks. I am Thuo, a professor from the Research School of Physics at Australian National University. Today we're continuing on that ICANX Talks in May, and it's our great pleasure to have our good friend in ICANX and also one of our moderators, Professor Martin Thuo, to be the presenter. So also because Martin is really stepping to rescue for an urgent change of our speaker tonight, who had family emergency, who couldn't make it tonight. So Martin has stepped in to help. And in this case, we also have a bit less number of panelists. So we have Professor Chao Zhou from Nanjing University of Science and Technology to join us in the panel later on. So firstly, let me first introduce our speaker, Professor Martin Thuo from North Carolina State University. Martin is a professor in the Department of Materials Science and Engineering at North Carolina State University and a co-host of the ICANX Talks. Prior to NCSU, he was the Sheffer Professor at Iowa State University. He was also a Meyer Pfizer and NSEC postdoc fellow at Harvard University. He is the recipient of several awards, including the ACS Nano Rising Star MSE Excellence in Research Award, Lynn Anderson Research Excellence Award, Black Vitek Batch, Faculty Fellowship, among others. His research interest encompassed the general theme of frugal innovation through surface interface thermodynamics. So Martin, please, the stage is yours.
Okay.
Yep. Thank you very much. Thank you for the introduction, and thanks everyone for coming in. It's a great pleasure always to be on this stage and to share some of the works that we're doing. And today I wanted to share some very fundamental science that we're doing in the lab and in the theme of frugal science. And I want us to take a journey into how we can understand sub-nanometer properties of a material by using simple droplets. And that is a simplification of saying that whenever you introduce a droplet to a surface, you have to establish equilibrium. So there's some strong thermodynamics underneath all that discussion. But before we get started, let's actually look at some understanding of self-assembly. And I didn't do the work, so the people who did the work are the ones highlighted in red here. This is my group at NC State and previous members. And if we think about nature and self-assembly, we can argue that nature, by a large extent, is a product of a lot of self-assembled systems. If we take the example of something microscopic like a tree, we see that as you break it down at different scales, you can see how at each scale, every component is put together through autonomous processes. Starting from the fundamental molecule, the glucose, this is a D sugar, the same sugar we put in our tea and in our food, only that it's polymerized. And once you organize it this way, it can form bundles, form fibers and microfibers, and then you start creating complex matrices that then assemble into cell walls and other organelles in the system that eventually give us a tree. Understanding this self-assembly allows us to explore technologies like what I was showing here in this video, things like paper-based microfluidics. If you understand the structure of the cellulose, you can control its wetting. You can organize it to be able to flow different streams of water above each other. You can control their behavior while they're in flow. Or you can actually start making new architectures that are based on this organization that we see here. And here I'm showing some work from Timothy, who has a French company that is trying to make transparent or adaptable wood. Here you're looking at oak veneer that has been trapped in a polymeric matrix that allows it to retain its beauty and give you some level of transparency. But as you look at all these screams of scale. If you look at a tree from the macroscopic scale, you don't actually quite right away understand the assembly of the cellulose or the organelles inside that material. And if we take a deeper look in nature, we see that this is not just unique to the macro scale of the organism. Here, we are looking at the skin of a shark fish, and these kind of patterns allows the shark to swim better. It allows it also to avoid anti-fouling. Other materials or other organisms cannot attach very well to the skin of the shark. Here, paying homage to my home continent, Africa, we see the Namibian beetle that survives in the desert because it has these very nice, well-organized hydrophilic systems that allows it actually to drink from the fog that comes in the mornings in the Namib desert. Taking a further look, in the deep sea, you see organized structures like this. This is a glass structure, but this structure here, the way it's organized, it makes it really, really strong to protect the sea sponge. And this material here, although it's made of glass, it's actually capable of holding way much more weight than we can actually achieve with our traditional way of fabricating glass. And not only in terms of structure and feeding and protection, we also see this coming in generation of color. The morpho butterfly is famous for its very well organized structures that allow it to generate this blue hue without using any dye. So nature is full of this complexity. If we zoom in even at a different scale, we can see and wonder at the beauty and the kind of structures that proteins form. These are peptides that are polymerized, but then based on how they organize themselves, they can form secondary structures that are beautiful and very complex, either as a singular unit or as an organized complex. And they can appear in different types or forms, the beta shears and the coils. And as you the macromolecular systems, you find such beauty that self-assembly gives you that we wish as we can emulate. But the question always is this all we can get? And how can nature do such wonderful work that sometimes we have difficulties even understanding or even replicating? If you look at man-made structures, we have succeeded in doing some quite a little bit of self-assembly ourselves. Here, I'm showing some examples from John Eisenberg's lab at Harvard University, where they're adopting capillary-driven self-assembly of soft pillars, and they can use that to even encapsulate component inside these pillars. We can also go away from fluids because also plants use a lot of fluidics to do the self-assembly. And in the man-made environment, we can start using light, where we use polarization of light to control organization of materials to create structures that are quite elaborate. And we've seen this even invoked from either covalent structure or secondary bond-driven or interaction-driven systems. And here I'm showing the example of molecular machines, where you can synthesize a molecule like this, where the central axis here is acting as an axle, because these bonds are being triple bonds, they are 180 degrees from each other. And this central unit here can rotate, allowing it to give you significant motion as you would in a regular motor. And we see also the proposal of putting together things like molecular machines. Here I'm showing a molecular planetary gear that is proposed by Drexel. And these kind of systems can open unprecedented capabilities. But how do we realize this stuff? What is our play space? We can either take a top-down approach or a bottom-up approach. And here I'm pulling some reference from Ludovico Cadamartri's work on programmable self-assembly, where they argue that one of the most important things is to empower your components with information. If you have informed components, then your assembly can go to any dimension you want, and you can actually then program a set of starting materials, whether they are molecules or they are crystals or small adducts, that then can self-organize themselves into very complex structures. And what this does to us, it brings this idea of emergency. You start with very simple components, but then through the self-organization, then you get these very complex structures. But fundamentally, when we go to molecular systems, we have very limited tools because those systems are going to be dependent on the molecular property, fundamental of which is the van der Waals forces. These are quantum-based oscillation in the electron density that induce dipoles in the molecules. And when those dipoles are aligned in a head-to-tail fashion, you can get some attraction between the systems. The other thing is that we can introduce systems that have asymmetric distribution in electron density, permanent asymmetry, and that can force this kind of system to either organize into head-to-tail fashion, as I'm showing here, or in the opposite. If you can imagine something coming on top, it would have the opposite orientation. And therefore, this brings the idea that you need to be aware of the plane of reference that you're looking at the assembling system. Other secondary bonds like hydrogen bonds and agentophilic bonds can also become very useful. And each one of these, you'll notice the strength increases as you move from the probabilistic Boltzmann type motion or Brownian motion based stochastic processes to the more engineered systems. And of course, if you can make mechanical bonds, you can actually make molecules loop across each other, and that can create some significant amount of strength in the assembled system that you're trying to put together. And using this, we see some very elegant assemblies, and this idea of emergence, this idea of putting things together, and then they energy minimize to give you surprising complexity, as is shown here in this simulation of a complex peptide assembly from the Molecular Foundry in Berkeley Lab, where when they put this peptide together, they realize that there is a layer somewhere in between here that is completely hydrophobic. And of course, you see on top of that, you see the charged species all coming towards that side. And this is coming from macromolecular self-assembly. So how is this even possible? How can we even make this predictable? And how do we even understand all this emergent behavior? And do we have the tools to understand how these molecules are interacting at one bond at a time? That's why my title is Sub-Nanometer, because we're trying to think how we understand these assemblies one bond at a time, and doing so without using very complicated or very advanced tools. The interesting thing about macromolecular self-assembly is that you can get a variety of structures. So this could be one of the ways to understand them. For example, here I'm showing two polymers co-assembling, and based on the concentration. The structure you're getting is actually dependent on the concentration. But even going back to the first image I showed you on the self-assembly of cellulose, in that image, I oversimplified what is not so obvious to a lot of people. That if you have a cellulose, you end up having two sets of properties. One side of that cellulose, if you look at it from top down, basically you're looking at the open side of the chain, you will be presented with all the hydroxy groups on that cellulose, and that side becomes hydrophilic, it's water liking. However, if you take a 90-degree view of the same chain, you will see that you're presented with the hydrophilic plane, meaning that this side of that chain will not like sugar. So we will not like water. So if you think about each chain, you can actually now start understanding where these kind of behaviors are coming from, or how these kind of behaviors are coming from, because it's all about free energy minimization. But these are very complicated systems. The systems I want us to look at is much simpler. It's where we take a simple hydrocarbon molecule and we covalently pin it into the surface of a fairly flat surface. And here we're going to use Carnage metals. And these constitute what are called self-assembled monolayers. And I say these are simple, and I put it in bracket because, as you will see, in the simplicity, there is an emergent level of complexity that this cartoon here does not reveal. And if we don't understand, or we don't quite comprehend the properties of this system, how then do we even think about understanding complex systems like this, or even complex systems like we saw in the organelles of trees or proteins, as I showed you before? So let's take a journey into self-assembled monolayers and see how we can actually use these systems to start understanding their assembly and their property based on a single carbon-carbon bond, and how that can become a big challenge in developing new technologies out of it. And why do we care about self-assembled monolayers? As you might be aware, last year the Kavri Prize in Nanoscience was awarded to these 4 gentlemen for their work in self-assembled monolayer. This is an old science. And actually, the field of self-assembled monolayer is much older than this, because it started way when Dutch sailors figured out that if the water is turbulent at sea, they need to add oil and add it in small bits so that they can calm down the storm. This was later picked up by Benjamin Franklin in his famous work on England ponds, and he is the one who then confirmed that and published it, but it was very well known by Dutch sailors before he picked it up. Now, from those very early beginning, we started using different substrates instead of using water, and looking at the so-called Langmuir monolayers, to more physically monolayers where we can attach molecules on a surface, and that's what this 4 gentlemen here brought to us. And that has accelerated advances in so many areas, as captured by the number of patents that we have seen in the diversity of field that we see this technology of chemi-solved monolayers playing a role, from electronics to batteries, to dyes and sensors, and there's a lot of work actually on sensors and optics. And this is in part due to the work by George Whitesides, who really pushed the application side of this, and conflict of interest. I'm a former postdoc in his lab, so this is where I picked up most of this knowledge. But if you look at where we are beyond what is captured in that in those patents, we are moving actually beyond some of those industries to start applying self-assembled monolayers in electronic devices. Here I'm showing an example from Chris Nyhouse's lab in Twente, where they have made a very high electrifying system based on ferrocene molecules. There's also work coming from a great lab in Canada, where they're using the self-assembled monolayers actually in distorting sound and manipulating the sound that comes from a guitar by passing current through those monolayers. We've also seen other advances in thermoelectrics from Yoon's group. We've work also from here in North Carolina, from Chichi's lab, on quantum tunneling and the role of a single atom in that. And more general, there's a lot of work, as I mentioned, in the patent that is based on these sensors. And here I'm showing some work based on a coupling of monolayers with some plasmonics to create sensors from a Tishal Tubes lab in EPFL. But my focus in my lab is more interested in molecular electronics. And with molecular electronics, we assemble these molecules on a surface, and then we try to build a circuit over it. And an example here is where you grow the monolayer, and then you put a layer of graphene, and then on top of that, you deposit gold contacts. And this is from Takili's lab in SNU in Korea. And the question always is that what is the role of the orientation of that molecule in the electrical behavior of that device, of this complex device? And given that you're working in an assemble system, does it matter how one molecule is oriented, or is it okay that we can assume an average? Well, it turns out that the organization of the molecule is very important, as shown here, that you can actually control the direction of the diode by the positioning of that one component. And what Chris Nyhouse and his team were able to show is that the conformation also plays a very significant role. And the beauty with that, or the interest in the use of self-assembled molecules, is that you can start installing functional groups like this ferrocene to do all sorts of different things. So the molecule can be very well engineered. We know how to make this, so we can engineer the properties very, very well for electronic devices. But the question always comes is, what is it that we're putting on the surface? Is it always as beautiful as this cartoon shows? How is the organization? What is the component density? And how do we tame the chaos, the vibrations? Because these molecules will not stop rotating simply because we want them. They're moving all the time. So how do we deal with that chaos? And how do we connect components to it? And more importantly, how do we contact a single molecule to be able to measure the current going through it? And is this kind of contact, where we put a solid material on top, actually capturing the true dynamics of the molecule? Or should we use something like a liquid metal as perfected in Whiteside's group and by various groups around the world? So our question here, our challenge is to understand that simple question of contact. Because unless we understand what is right on top there, we cannot really delineate the charge transport or the performance of those materials. So we went back to the basics, and from the work of Jacob Sagiv, 1980, where he talked about this monolayers, we started seeing things that were interesting to us, and the chemistry curiosity was very obvious. Here, Sagiv used these trichlorosilane, and he hydrolyzed them with water and then put them on the surface to create what he says is something like this. However, this structure has a problem. And the biggest problem is that if you look at the silicon-oxygen bond, it's only 1.8 angstrom, and the bond angle here is 105 degrees. And therefore, the space created by this creates a cylinder of only 2.9 angstrom diameter. To accommodate these two chains to form a monolayer, you need a cylinder that has a diameter of 4.9 angstrom. So it's not possible to get these organized as straight, well-assembled monolayers like this. And this question was not unique to us. Others have looked into it, and we have seen a lot of strain associated with these kind of bonds. And of course, Nick Spencer showed using refractive spectroscopy that I actually don't get a monolayer like this, but you get these weird carved arrangements on the surface to buckle, to extend this space to allow the chains to exist. And later on, and the Nick Spencer used silicon surfaces. We used paper as a surface, and we showed that actually when you have that texture, these materials can actually grow into very large clusters of silanes. So we start the monolayer story on a very challenging field. But it was not just the Sagiv work. The initial work in the 90s that came on the characterization of the wetting properties on the monolayer, the data was all over the place. Excuse me. You start with the work by Whiteside and Porter, and you see Whiteside says the contact angle increases in an exponential manner as you change to longer and longer chain lengths. And then we see that Porter claims that as you get that exponential growth, you get to a point where you start seeing an oscillation, which he called the odd-even effect. He claimed it's due to the asymmetry in the orientation of the top carbon based on the bonding of the single molecule at the surface. And I encourage everyone who's interested to look at the literature, because the claim that was made at that point, the discrepancy, is that most of the work that was done to show this odd-even effect was most likely due to adventitious contamination. However, from a chemistry point of view, if these molecules are well ordered, as shown before, we should expect to see an odd-even oscillation. Why? Because the bond angle between the even and odd numbered carbons should be oscillating. It should be putting that terminal CH3 degree in different direction. And so the odd even is to be expected from a pure chemistry point of view and perfectly ordered sum. But here we see in 91, there is no clear agreement as to whether this is an observable phenomenon or not. And even the people who came after that, they did not show anything that either confirmed or disputed that. The data that came later was all over the place. So who is correct? Are we getting well-ordered monolayers? Are we getting this odd-even effect? Or what is going on? And so we believe that we can actually use simple droplets of different liquids to actually reveal what is going on at the bottom of that monolayer. And as we change the structure of the surface and the structure of the molecule, the free energy equilibration of that interface should reveal the nature of organization of those molecules. And then we thought that if that is the case, then we can confirm the data using spectroscopy or other secondary methods. And so to understand these self-assembled monolayers, then we need to tame the complexity, and we need to define exactly what is the sum. Is it really perfectly ordered? Is it really disordered? Do we understand the fundamental forces that are operating in making the sums? And can we exploit these forces to reveal their organization? And I believe that we can use simple equilibrium understanding to define or to understand how these forces are equilibrating and therefore reveal the structure of the sum. And the first thing we did is we need to do is to understand the surface. So we need to control the surface property. And here we will focus on roughness. The first thing, if you evaporate any of this gold, any of the gold or silver, they always give you the 1-1-1 orientation. So that is fixed. The bond, the chemistry is fixed. Gold will orient the molecule at about 30 degrees, while a silver will orient the molecule at about 10 degrees. Then the question comes, do we have surface mobility? Is the surface reconstructing? And is the roughness going to be an issue for us? And we focus first on the roughness because we believe if your surface is very unevenly textured, then it's going to be harder for you to control that assembly. And if you look at these two surfaces here, you see one is very grainy, has very, very fine points, and is also rougher, while this one has a lot of larger flat regions, and the average roughness is much, much lower. And when you look at this from a different perspective, you can see the difference in the surfaces. This is very similar to what was used in the 90s. This is what we have been able to develop in more recent years that is much smoother, and the roughness is approaching the length of a carbon-carbon bond. So within 1 or 2 carbons, we should be able to overcome any surface asperities. And when we do all this, then we can actually bring free energy as a tool to understand what is happening in the monolayers. So we try to tame even if we tame the complexity, then we have another problem. Do we really know what is going on? Do we then have a question of a measurement problem? Is what we are measuring really a representation of what is on the surface? And then what we need to do then to get coherence in this measurement, then we have to think about bringing convergent tools to tell us what is happening at the surface. So I will share mostly about our work on droplets, but I will also show you how we confirmed it using sound frequency generation. And these two are very different and decoupled. And therefore, if they're giving us to the same point, we believe they are pointing to the truth. But then we always have, as scientists, we always have the challenge of understanding what the reality is. So I do expect that the younger scientists who come after us will find new nuances in our works, and they will help advance the field. So the first thing we did was to look at how we prepare metal surfaces. In the 90s, everything was deposited. Then as deposited, and it was very, very rough. Then we started using chemical polishing, thermal annealing, and then temporary stripping became one of the most reliable for getting flatter surfaces. But we sought ways to improve this so that we can get even smoother surfaces, because the roughness here is about 0.4 nanometers. It's still fairly rough compared to the length of a carbon-carbon bond. And our approach was we were able to make surfaces that are of tunable smoothness by actually adding an add layer to the gold. After we deposit a second metal on top, and then that allows us to introduce interfacial strain. And that, because we don't penetrate the gold film all the way, we only cause strain defects. Those defects propagate and reconstruct the surface without changing the faceting. And we can tune this roughness very well depending on what add layer you add, whether you add aluminum. You don't make a lot of changes to the RMS, but as you go to things like iron and titanium and zinc, you get fairly smooth surfaces. And we can model this based on the redox mismatch between the two and the lattice mismatch, and we can predict where the surface is going to be, and it's very tunable. Now that we have that, we now compared our strip surfaces and as deposited gold, and we saw that when you have a rough surface, you get the same results as what was observed by George Whiteside. And when you have a smoother surface, the temperate strip, you now start seeing the emergence of this oscillation, whether you have gold or you have silver, right? And after this, we confirm this using SFG. When you have use some frequency generation, which is very surface sensitive, and you see when you have a surface that is 0.4 nanometer in roughness, you see the CH3 vibration, antisymmetric vibration actually splits between the odds and the even because of the average orientation on the surface. When you have a rough surface, then you don't see any separation between the two clusters, which means that the difference between what was observed before and what we are observing now with smoother surfaces is because of roughness. So roughness is critical in understanding this. So instead of using an advanced method like SFG, you can actually use contact angle measurements, drops of water on the surface to actually reveal the order and the orientation of that terminal CH3 group. And now that we can show the difference between an orientation in this direction and this direction using contact angle and using SFG, what else can we get in this? We observe that the roughness of the surface plays such a critical role that as you get to a gold surface that has a roughness of 1 nanometer, this ability to distinguish these odd and orientation in CH3 group disappeared. And we call that the theoretical limit to the odd even observation. We also did some theoretical work that allowed us to actually distinguish between between substrates, whether we have gold or silver, and we can see because of the cant angle, the orientation along this axis, gold gives you a significant larger difference between the odd and the, because this signal is dependent on the cosine of the angle in which the beam is meeting the CH3 bond. But in silver, where the suns are a little bit more upright, they're about 10 degrees, that angle is much smaller, and therefore you get a smaller spacing in the odd even effect. And this is confirmed through wetting studies. So from what you get from a 750,000 instrument, you can also get the same information from a droplet of water, 5 microliters of droplets of water on a surface. Now that we have shown that, we wanted to get a little bit further and understand this dynamic. And we took our wetting data and we said, if you spread the work of addition between the London dispersive forces based contribution and the contribution due to the polar forces, then you can be able to deduce a parameter here that is based on the proportional contribution of each of these forces. And if you plot that against the number of carbon, you see these very beautiful exponential decays, where for the even numbered molecules, you see there's a fit parameter of 4, while for the odd numbered carbon, their fit parameter is 3. And we ask ourselves, does this have any correlation to anything we know about chemistry? The other thing that we notice is that as you get to higher and higher molecular chain, this plateaus out, and we believe this is where the suns become crystalline, and that allows them to be completely symmetric in the odd even effect. So the asymmetry in the odd even effect actually is telling us something else. So given this, we go back to chemistry and we try to see what this even and odd parity means. And we see that if you take a hydrocarbon and you put it in free space and you allow it to conform itself, you see that for even numbered carbons, they make this hairpin at a certain length. They try to maximize their intramolecular interaction, and they make a turn that is 4 carbons in length. However, when you have odd numbered hydrocarbons, they will use a 3 carbon turn, very similar to what we are seeing here, 3, and the 4 that we are seeing here. So we see a correlation between what we are being able to pull here and what has been observed in gas phase studies. And, and for the sake of time, let me just fly through this. This is how we made the surfaces. We spotted the molecules, and we can see that it has nothing, the add layer we added has nothing to do with the monolayer that we're growing on this side. They never penetrate all the way through. And since we can tune this very well, we went ahead and started constructing silver also. But silver, because of the asymmetry in the construction, our faceting in silver is silver 111. But when you sputter this molecule and create defect, it will not reconstruct in the 111 plane. It's going to reconstruct on the 100 plane. And that allows us now to create more alpha surfaces, so we can extend our study beyond the 1 nanometer that we had been able to do before. But because of the temporary stripping, we will have a very good overlap in scale with that. And when we do that, we see that the odd even asymmetry is maintained in silver, but it's going to be smaller. And we also realized that RMS is not the best metrics to actually measure the roughness of the material. The bearing volume was more informative because it's looking at the total structure of the defect rather than looking at a single hypothetical line in the average. And when we use the bearing volume, we can actually be able to distinguish where the differences between gold and silver is coming from. And we see that actually the biggest difference between them is due to the even numbered material. The odds are very, very close between silver and gold. And from here, we can actually see if we change the solvent, this odd even effect is not always there. When you have hexadecane, we see the odd even effect throughout. And hexadecane has no polar component, it's completely non-polar. But when you have polar solvent, you always see that in the silver, you only get the odd even when you have a smoother surface. So what is going on here? Can we then use the properties of the solvent as a way to probe the structure of the SAM, and actually the role of the substrate on the SAM? So far, we have been able to see that there is a theoretical limit, and we will be getting a little bit into the role of roughness in a little bit. But I wanted to kind of provide a small summary here that even from these very early studies, we can see there is a limit to us being able to distinguish the odds and the even, whether you have silver or you have gold. The other thing that we have observed is we observed that there's an evolution in the contact angle that actually indicates to us that at a certain point, from C4 to C8, you're not going to be able to see any odd even effect. The increase in hydrophobicity is linear. And then you get into this window here where the odd even becomes asymmetric. And by the time you get to C14, the odd even effect is completely symmetric. And then you see when you're in very, very short monolayer, the contact angles are actually pretty low, which is very surprising. How can I put a hydrocarbon on the surface and get a contact angle below 90 degrees, meaning that monolayer is actually wetting with water? There's some interaction between the early carbons and the metal that allows it to be so polarized that actually the water will spread very well. And this crystalline here correlates to the crystallinity of the SAM. This has been observed actually by a group in Australia, where they showed that as you increase the chain length, you're reducing the defects in the monolayer and you're getting more crystalline. But we can reveal this evolution in structure using droplets of water. Now that we know that different solvents play a very big role, we started now looking at the ratio of the gamma P to gamma D, the polar component to the dispersive component. And of course, for hexane, this is 0. This is completely non-polar solvent. And for water, it's about 2.3. It's very, very high. And when we measure the contact angle, we see that when you have very smooth surfaces, you always see the odd even effect, irrespective of the solvent. Now, when you start increasing the surface, you start to see some things like formamide and diethylene glycol and glycol, they fall off that line. They don't show you the odd even effect. And as you go there, the effect is dying out. And we started asking ourselves, what exactly is going on here? What is it telling us about the structure of the SAM? And we crafted a parameter, sorry for the long equations, But I would, if you want to know more details, I'll refer you to this paper here in Angevante, where we say, now let's look at the absolute cases and compare the contact angles between the contact angle of the odd or even when we have an odd layer, so the surface has been engineered relative to the absolute where the surface has not been perturbed. And we look at the difference between the odds and the even, and we define this new delta term here that allows us to kind of summarize the differences between those two. And when we look at that asymmetry and we compare it to the gamma P, gamma D, we see this really interesting asymptotic behavior, where if I have an RMS of about 1.9, I see that I get a double dip in the property, meaning that there's something dominating the behavior on one side of this gamma P, gamma D, and another effect dominating the other side of that curve. And we see these changes as I change the roughness of the surface. And we try to use statistics. I'm not going to bog you with all the numbers. We started using unpaired mean differences to try and reveal what is playing a bigger role. Is it the gamma P, gamma D? Is it the interface? Or what exactly is going on? And just very briefly, if you look at a hexadecane, you see as you move from very smooth silver to very rough silver surfaces, you kind of see not very clear linear behavior. But there is almost like a turn point when you come to the silver titanium. When we compare these as a polar solvent like Gracelo, we start seeing this gradual decay. When you have Gracelo, when you have water, actually that gradual decay even becomes more prominent. And so we wanted to see whether we can actually put this together into a single plot that can reveal all that is going on. We looked at the role of the asymmetry in the odd-even effect, and we see also the same thing. It's much, much more complex behavior than we had predicted. There are no emerging trends, except when you come to this 1.1, you see kind of an increase, but all the others, the behavior is all over the place. There's no dominant force. So what this means is that this behavior is a coupled behavior, and it's a little bit more complex than can be easily drawn out. And so when we take all this data and we make this 3D plot, and we look at the gamma P, gamma D versus RMS and the asymmetry in the odd-even effect, this is what emerges. It is actually like three different phases. When the surface is very, very smooth, there is no dip. But once you hit a certain critical roughness, you start seeing this crevice emerge in the middle, where now the data becomes dichotomous. One side above gamma P over gamma D, slightly above 1.0, which to us indicates if everything was balancing at gamma P, gamma D of 1, it will mean that the polar and dispersive forces are contributing equally. But we see a slight skewness just above 1, which indicates there must be some systematic bias to this ratio that is not 100% coming from the molecule. And we find that that's because of the molecular dipole. Once you attach the molecule on the surface, you will get a very small dipole along the surface normal, and that is what is skewing this data. But we see that when you have very smooth surfaces, that asymmetry does not emerge. But when you have rough surfaces, it becomes extremely clear that that is what's happening. And if you look, for example, at this plot here, if you continue pushing this, actually it will become like a concave. So it dips, comes all the way to the bottom, and then rises up again to almost the same behavior as here. And this tells us the dominant force here is completely asymmetric to the dominant force when you're on this other end of this plot. And so as we make more layers, the substrate roughness between about 1 nanometer and about 2.5 is extremely important, and we cannot ignore it. And we take this parameter and we take it one step further, And I'll start looking at this as, in terms of a histogram, and you can see almost very clearly that there's like a 4-quadrant type of behavior, and we call this the scarlet quadrant based on the postdoc who developed it in my lab. And what we believe is that when you have very, very smooth surfaces, the sum is dominating the property of your assembly. And when you have very, very rough surfaces, the roughness takes over and start dictating the properties of your surface. So the earlier work in the 90s was in this window here, while the smoother surfaces are starting to show us what is happening on this side. And as we introduce new solvent, we also have to be aware that the behavior of that solvent is dependent on the contribution of the polar and the non-polar component. And therefore, like I showed earlier on with the case of glucose, depending on what is the dominant form of interaction that you get, you can get very different responses. And that is what we see here. When the sum is non-wetting, when the liquid is non-wetting, meaning the liquid is very polar, you get one type of behavior. The forces are repulsive. However, when the liquid is non-polar, it's going to weigh these kind of molecules, and therefore it's going to have attractive forces. So the first bottom layer or shell of this quadrant here represents attractive interactions, and the top is repulsive interaction. And then, of course, this side here represents SAM's dominated behavior, while this side here represents surface dominated behavior. The other thing we observe is that with gold, our transition point was about 1 nanometer. With silver, we see our transition point coming at about 1.5. So the orientation, the substrates is important. The molecules you're putting on the surface are important. The roughness of the surface is important. And all those things must be considered if we are to understand the assembly behavior. And we summarize this in this very large cartoon here, and it's idealized where we are showing very rough surfaces behaving very similar to smooth surfaces, and of course the repulsive and attractive forces being orthogonal to each other. And with this, we can actually argue that a droplet can reveal sub-nanometer fluctuation in the properties of a self-assembled system if properly applied. And this parity effect, the odd and even behavior, is not a fluke. It's expected from a scientific point of view, from a chemistry point of view. And if you have well-ordered sum, it should be observable as long as the system is near ideal or the sums are allowed to organize very well. And of course, with this, we wanted to confirm our behavior using spectroscopy. As I mentioned, we had worked with gold to confirm the odd-even effect, but also we went further and started looking at the other smoothing surfaces to see whether the odd-even response to this spectroscopy method is going to also be dependent on roughness. And lo and behold, the same behavior is observed. As you change the roughness, you dampen the odd-even effect. As you make the surfaces smooth, you amplify that phenomenon. And so we can see a very nice correlation between what we're observing with contact angle and what we're observing with our SFG, whether we have gold or we have silver. The one interesting thing is that because the odd-even effect in gold is stronger, we also observe the same thing. The differences in the signal in silver is weaker than on gold. And of course, as we get higher and higher, we see the loss of that odd-even effect much faster in the silver surfaces than we observe in the gold surfaces. And of course, these are more grainy, they are more rougher, and so we expect them to be lost very quickly. We then also looked at theoretically the extent of that SFG signal, and we modeled as we change the orientation angle, what kind of signal we should be getting. And we were very happy to see that our theoretical calculations actually aligned very well with what we were measuring. The signal intensity that we were seeing was telling us that the sums that are very well ordered on those surfaces. And whether we consider just the cant angle or the twist angle, we see it's exactly as expected. We expect a tilt of about 28 degrees and a very small cant based on the cant angle based on the odd and even orientation. And we observe this in gold and also in silver, and that actually was very good for us. One of the things that we could not observe with the droplets that we observed in the SFG is this idea of ghost rotation. Ghost rotations are when these molecules twist within themselves just a little bit to cause this to be distorted a little bit. When you have ghost defects, you should see the asymmetric, you should see that manifested in the CH2 signal of the SFG. So SFG has that one added advantage that we can get finer details about the orientation of the monomer than we can get with droplet. And this was a surprise because it had been predicted that it should be observable up until you have C14. But on silver monomer, the more upright ones, we were not able to observe that at all. And then, the interesting thing is, why do we care about these droplets? Well, what I told you was the use of these monomers in molecular electronics. If you think about it, we are using liquid metal as contact. These have very high surface energy. They are very, very polar. So as we understand the interaction of the surface, it should allow us to understand how the liquid metals and the SAMs are going to interact. And we see this these manifest in terms of the interaction between the molecular dipoles and the liquid metal, and we see differences in dipole, just as we saw with the contact angles. And we can even extend this further with the hydrocarbon systems that we're using to show that the decay constant, the charge decay constant, correlates somewhat with contact angles that we observed, for example, with hexadecan, with the only exception being the odds were a little bit higher than we had anticipated. And we investigated this a little bit further to see whether we can actually see reveal other information that could not be revealed without understanding the contact angles. And here we use these different product groups to show that actually, unless you go deeper into statistics, you cannot understand this behavior. If you just measure average current density, you will get that these molecules are similar. But if you pay attention to the current changes and evolution with applied force, those similar interactions that we had before, you start revealing very new information, and you see the dynamic behavior. Putting that liquid metal on the surface, you start revealing dynamic behavior of the monomer, between all of the press, and it manifests in the skewness of the data that you're obtaining. And with things like this, where the dipole is kind of oriented at an angle, you see an oscillation at low bias, it then gets stabilized as you go to higher bias. So that interaction is very, very important. We could further evaluated this using open and closed head chains on our molecules, and you see emergence of clusters of data that tells us these materials are being very dynamic. And you can summarize this and correlate this very nicely with the fundamental simple organic chemistry understanding of these 4 functional groups, where you see this has the lowest mobility. So you see very little unpaired mean difference between an odd and an even. While this one here, being a cross-link and also 3 carbon, will have a very, very strong, large spatial displacement. And we can see this odd-even effect getting amplified as you increase the degree of freedom. And we also see that we change, depending on whether I have an even spacer or I have an odd spacer, I can either influence the enhanced conductivity or enhance resistivity, which is very telling in terms of the performance of this molecule. You change 1 carbon, you get the orthogonal behavior, even though you have the same functional group on the molecule. And in conclusion, I want to say that when we look at self-assembled systems and we try to study them, ideally we want to assume they're very simple. But in fact, if you pay attention to them, there's a level of emergence complexity that comes when you put these clusters together. Things like the odd even parity that I've shared with you, things like dipole, domain structures and grain boundaries and all those kind of stuff. Defects on the surface all contribute into this behavior. And therefore, we should exercise caution in oversimplifying very simple system. And nature has mastered all this to be able to deliver some of the elegant materials that we have seen before. And not only should we pay attention to the monolayer, we should also pay attention to the material we introduce into contact this monolayer. And with that, I want to acknowledge the funding who have funded the whole lab throughout the years, and collaborators, the students who do the work, and the organizers for giving me a chance to share this work with you. And with that, I want to say thank you.
Thank you very much, Martin, for a fantastic, fascinating talk about the surface assembly. So let me now, before, well, we should actually introduce our panelist tonight to bring her onto the stage, bring him, sorry, to the stage. So our panelist is Professor Thuo from Nanjing University of Science and Technology. So Dr. Chao.
Hi.
Sorry, yes, yeah. Let me introduce you first. Yeah. Okay. Dr. Thuo is a professor in optical engineering, Nanjing University of Science and Technology, China. He leads the Smart Computational Imaging Laboratory at the School of Electronic and Optical Engineering, NJUST, and is also the founder and director of the Smart Computational Imaging Research Institute of NJUST. Professor Thuo has long been engaged in the development of novel computational optical imaging and measurement technologies, with a focus on phase measuring imaging metrologies. With he has published over 200 peer-reviewed publications in prestigious journals with over 11,000 citations. He's also Collaborate, highly cited researcher and fellow of SPIE and Optica. So welcome, Professor Thuo, and welcome you to the stage.
Okay, thank you for the introduction. Hello, everyone. I'm very glad to be here.
So of course, the first question goes to you. We have a bit of less number of panelists tonight, so so please go ahead, Chao, to your first question.
Okay, so I think thank you, Martin, for the very interesting and instructive talk. Because I'm not an expert on this material nanotechnology, so can you brief induce? Because we know that assembly technology has been applied to the optical sensing and imaging. For example, we have some PMMA microsphere. We can do a self-assembling to make the microlens theory for imaging, especially for integral imaging, or we call it light field imaging. So I'm not sure can you show us some example? What's the applications? So mainly for this kind of self-assembly molecular techniques, especially for your gold surface. So what's the purpose for fabricate such kind of the self-assembly service? So do you have any potential applications, at the sensing or optical imaging applications? So you can manipulate the light field for some imaging purpose?
Yep, okay. So the key thing I was discussing today is there's a lot of knowledge on self-assembled systems, complex and small.
Yes.
But the biggest challenge we have is that we take that information as a perfect truth. For example, when you assemble your spheres, you assume the sphere is perfectly smooth. So when you bring any interaction between your sphere with any material, the assumption you make is that contact is simple. What I was trying to show you today, it's not that simple. And if you pay attention to that simple interaction at the interface, you might be able to start pulling information that you did not expect to see. For example, I showed some slide where people are using self-assembled monolayers for sensors, optical sensors, right? So you put the monolayer, you put your protein in there, and then you shine light, and you expect the response to be independent of that monolayer. What I was actually trying to illustrate is that if you don't pay attention to the orientation of that molecule, I can change one carbon and your signal goes haywire, right? So in the last section where I was showing, I didn't have a lot of time to dig into that. Maybe I can share that again and just show you what I mean by this. If you take these molecules, for example, this very simple head group here. I take this simple head group. This is a very small molecule. A lot of people wouldn't even care when they're doing like sensor development about something like this. However, if I put 10 carbons below it or 11 carbon below it, the behavior is completely different. If you take your measurements using a 10 carbon molecule and you're measuring conductivity, at higher currents than somebody who is measuring it on an odd spacer, 11 carbon or 9 carbon. Something so simple, yet we don't even think about it. The 1 carbon, which 1.5 nanometer, can really shift the behavior of your measurement. If you go back and look at the work that is being done on charge transport, right? People are starting to start thinking about, hey, I can also put a photochromic molecule, photoactive molecule, and I can use light to excite this and reveal a completely different behavior. But if you don't pay attention to the number of carbons you have in that molecule, how they are oriented, that simple 1 nanometer orientation can make all the difference in your behavior. You see other people saying, okay, I'm going to put 3 carbons on a gold surface, and that should be enough to make it insulating. No, it's not going to make it insulating because it's so close. The interaction, you have to pay attention to the interaction between the metal surface and the carbons you put. And what we observed is that if I have 3 or 4 carbons sitting on a surface, guess what? Those hydrocarbons are hydrophilic. The water will spread on that surface like there's no hydrocarbon. Yet, if you increase the number of carbons, you start seeing this hydrophobicity. So when you're doing imaging, if you're working with any organic molecules, and if you look at where I started with when I was talking about the polymer self-assembly, those structures are so complex, like what was shown by the Bakri group. You put peptides on the surface. Peptides should be hydrophilic, right? Proteins interact very well with water. But when they make a film out of it, they reveal a completely hydrophobic area. There's a region where you cannot put water there. The proteins don't want to interact with water at all. Look at the molecule itself, you don't see that. So agent behavior that we need to worry about when we're acting with organic molecules. We have to dig a little bit deeper and let us not just assume that this is all known, it's all old science. Like I showed even from the work with the if you look at it very carefully using simple chemistry, you start seeing things don't add up. It doesn't make any sense that it was ammonia, and it should not be, right? And actually, in that paper, I didn't even get to discuss this a little bit. They used Jacob used water to hydrolyze his molecules, but from a chemistry point of view, you put those silanes in water, they will cross-link because it later uses the same reaction of OH with the silane to form the ammonia. So there's a lot of questions in literature that needs to be clarified, and the work is not just poking holes. And the challenge is we always move towards complexity, stepping back a little bit and saying, do we really know what we're working with? When you're doing imaging and you use that polymer bead, what exactly is happening between the bead and whatever material you're working with?
So Martin, keep going. Sorry, go ahead. Yeah.
It's quite hard to actually to simulate the magnetic wave when light pass through for example, the PS max spheres. We use FDDT to simulate the whole process. But actually, the topic you discussed actually is in much smaller size, so we can see the molecular orientation. So how you can infer the orientations interaction? So actually, I think it's quite indirect method. For example, the angle is slightly changed. So how you can characterize this by using spectrometry or so actually, I think we cannot infer it. We cannot see it directly, so we can use some indirect method to get this field, to get the structure and the how do you see the nanostructure, because actually it's quite sensitive. The angle is quite smaller, small change. Expand more on this specific structure.
Yep.
More process.
So that's the whole point. This is why I was talking about Frugal science, right? We compared our data with sound frequency generation. So the sound frequency basically generates two beams. You have an IR beam and you have a visible beam, and then you combine at the point of contact. If you focus that beam so that it's just on top of the monolayer, the generated signal, the SFG, the sound frequency generated signal, will tell you about the orientation of that bond. But what I was,
because I think the sensitivity should be very high, because it's
really it's very precise. You can see actually an interface layer with SFG, and we can pinpoint exactly because it's so sensitive to the angle in which the bond and the light meet. We can actually see the resulting signal tell us exactly, are we oriented in the right way? And you can actually predict even the intensity of the signal by a very simple calculation. Because this is polarized. You're bringing in polarized light. It's not like unfocused or unpolarized light. It's very, very well oriented. So you get very clear directional data. But what I was showing is that, okay, you can do an experiment like that. That experiment is difficult, it's complicated. It's not for everybody. Nobody has a $750,000 to buy an SFG. But what I was saying is, if you understand the molecules you have, and you pay attention to how things are interacting with each other, you can actually reveal that information, or a good chunk of that information, without requiring an SFG. You can actually expose your material to different liquids, and you look at the wetting behavior. And because that wetting behavior is operating at a sub-nanometer scale, it's a thermodynamic molecular equilibration that gets manifested in macro scale, you should be able to pull information out of it that is going to tell you about the behavior of your material.
That's my actual question. Just to clarify, you're basically developing this quite a universal sort of technique. You recommend that if you do wanting to use this self-assembly technique for any particular application, you should pay attention to that to understand what molecular orientation is, what that implication, the further behavior, electrical, optical behavior of your system, whether sensor or electronics. Is that what you?
Yes, exactly. That's the whole message. Basically, our message is take a break. Stop rush to fancy stuff. Go back to fundamental, because this is nothing new. We are not, the science is old. This is Young's Dupree equation that we are using. But pause and think about what you're doing. Use the simplest tool you have. Bring your material in contact with a drop of a liquid. And if you follow how that liquid is behaving, it will tell you of the equilibrium state of the molecules you have on the surface. It's as simple as that. But we have gotten in a chase of making more and more complicated techniques, but we don't sit back and look back and ask ourselves, is the tool we are using actually what we claim it to be? Are we actually building on something that we don't even understand? Right? And these very simple monolayers are an example of, since 1980, we've been spreading monolayers everywhere. But what we are saying is that, no. Sit back and think a little bit. Pause and think. Yeah. So yeah, and especially for people who are developing sensors and you're dealing with optics and electricity, you need to be extremely careful. Because
Definitely.
every time you put an organic molecule, there's so much going on.
That's exactly right. It's quite scary, I think, sometimes. I have a question about, because certainly you're trying to reproduce some, really look into the details of the traditional old measurement.
Yeah.
And is that the reason why you're using gold and silver substrate? Because you can, compare and look at old data and also understand fundamentals. But for also maybe traditionally those are the surface that you can get quite smooth surface. Maybe that's the reason. My question is about are you expecting similar behavior, or you actually thinking it will be more useful to also explore other surface like the semiconductors, the 2D materials can be very thin and can be useful further study?
So a little bit of history, and especially for the young people in the audience who are starting their career. I did not do this because I wanted to do it. I did this because I failed, and I failed miserably. I was interested in molecular electronics, but when I started taking measurements, I realized my data does not make any sense. I'm like, what am I seeing here? This is because we started seeing that odd-even effect emerge in 2011. And I started looking at the literature, and I got more questions than I got answers. So I started now peeling back. So we have started now going back to the gold and silver, first because I wanted to make sure that I'm not crazy, that my data was okay. And then once we have gotten comfortable with that, now we're starting to explore into other materials with a little bit more understanding. But with the flexible 2D materials, anything that is flexible right now, it is way too complicated for us even to think about where we would start. Because the moment you introduce curvature in any system, you introduce pressure jump condition. How is that pressure jump condition going to affect that? If flat surfaces have bred us to that crazy big cartoon that I showed you with a very asymmetric behavior, if we introduce that curvature, what is that going to do to those molecules? How are the molecules going to interact with each other? And what is the that is going to be needed for us to retain the interaction compared to a very high temperature where the molecules are almost independent? So it's a good question, but I don't have a.
Yeah, I was just really looking at the surface smoothness and all this future probably for the applications, right? It's quite interesting, could be happening.
Yep.
That's but yeah, I guess I do understand that the curvature issue probably could be very complicated.
Yep.
So I have another question, because in our optical sensing and imaging applications, so the matter surface is kind of optical modulation, newly optical modulation device. It can change the property of the lights, for example, the phase, amplitude, polarizations, and give you the low applications. So can you make a brief, and I think a brief comparison between your self-assembly surface with a metal surface for optical imaging, for optical manipulation purpose? So I think maybe some audience, some students like me are not very expert in the material science, but we are very interested in its applications in optical manipulation and for the imaging and the sensing applications. So can you give some comments on this point?
Sure. And when I look at paper that use molecules like isobenzene deposited on the surface for either actuation or just a chromophore to absorb light on a complex surface like a metal surface. Now you can make that system, and you can make very advanced metamaterials with very interesting features. However, if you have organic molecules sitting on those surfaces, whether by choice or by accident, depending on which molecule you have, you can actually influence the behavior of responses. You can actually influence light polarization, for example. You can create rotations in polarized light, because some organic molecules, especially the chiral molecules, can actually bend incident light and change the angle at which you're seeing the light coming out at the other end. If you have very good absorbers, they can actually affect what you observe. Your measurement will be perturbed by the. Now, the behavior of all those chromophores is also dependent on the orientation and the distance between the surface and where the chromophore is sitting. And this is why I was showing the work by Hatice Al-Toub at EPFL. She does these beautiful sensors where she makes very unique holes to amplify the signal so that you can actually detect very low concentration through plasmonic enhancement. So if you make squares on gold, you can get like edges where you have a accumulation of surface plasmon, and based on the probe you have there on that area, it can actually amplify the signal that is coming from the binding event. Amazing work. But whenever I look at those kind of sensors, I always ask myself, what is the role of this little ligand you're using to attach the molecule on the surface on the optical response? Will I get the same signal if I change the number of carbons, if I change the orientation of the antibody antigen complex pairs? What if I rotate that molecule and make it chiral or achiral? Am I going to get a different response? And I don't know. And what I'm trying to persuade everybody to do is, if chemistry or material chemistry is not your forte, find somebody who's an expert in it. Let them challenge your signals. Let them open the parameter space, because only when we fully understand these systems are we going to be able to make lasting technologies. Yep.
Yeah, I think if you can make for example, the orientations and the molecule actually controlled by your technology, so it can manipulate the light field actively. So it's kind of a newly version of the spatial light modulator. We can control the lights, so we can actually, it's possible to create some new possibilities for novel imaging and sensing technologies, because we need to manipulate lights actively. Yeah. So currently the metal surface is not easy to manipulate. It's not easy to program. Mm-hmm. So for your technology, so can it be make, for example, the orientations actively? So change the orientation angle.
If you have polarized light, yes.
Okay.
If your beam is polarized, all you need is to put 100ness in your molecule, and it will bend that light.
Okay. So the light property will be changed accordingly.
Yes. Yeah. But if you have achiral, like for the molecules I use, they cannot. Those ones have zero effect on light, right? You're gonna just get refraction, and that's it. But you can, if you change that group and you put something that prefers to sit in a certain orientation, of course, it's like our hands, right? If I put a bunch of hands oriented this way, they can park next to each other very well. But if I introduce hands that are sitting this way, then they'll be facing each other. They're not going to give me very good orientation. So what you want to do on the surface is look for molecules that have 100ness, and then you assemble those. And if you understand how they're going to park next to each other, if you understand those interactions, then you can create a bigger cluster that collectively can really twist your light and give you completely different behavior. Yep. And actually, I would actually recommend you look at the work of Nicholas Kotov at Michigan. Okay. He makes these chiral nanoparticles that, you know, they only assemble in a certain direction. And then when you shine light into it, crazy stuff. Amazingly crazy. I love it. And I think it will answer your question, because it will show you how you can actually manipulate light by forcing molecules to assemble as a bundle with one oriented in one direction. Yeah.
Thank you.
Thank you very much.
Martin, towards the end of your talk, you talk about the using liquid metal and then that interaction. I don't think I fully understand what exactly you did there. So basically, can you just explain a little bit? You using the reason of using liquid metal is to replace the water droplet, or what is that? I might just get confused of what's that exactly used for.
So if you look at hexadecane, is non-polar.
Mm-hmm.
Yeah. Then we go to water is polar.
Yeah.
Metal is the surface energy is out of the roof. It's in the hundreds of dynes. Water has a surface energy of 73 dynes. So if you compare if we are getting such sensitivity by putting water, then when I put a liquid metal on these molecules, I should get even bigger drastic response. Right? I should be more sensitive. And that contact, if then I use the liquid metal to deliver current into the molecules, then that contact will become a huge influence on the amount of current that is going through. Right? And so if I have an odd or even molecule and I apply odd even number of carbons and I apply current, I see very similar behavior to what we see with the water. The odd even oscillation is very powerful and very clear. Now, then I change that and I put something else that is not just a simple tilt like this. I start now putting more complex molecule that will give me all sorts of conformation on the surface. And with those, I can reveal dynamics that I know from chemistry. So when I have those cross links and I start now bringing a liquid metal and I pass current through it, I can differentiate 5-member ring from 6-member ring, open and closed systems. I can differentiate all of them. So the sensitivity is much better. Yeah,
right. That's really interesting. So what types of liquid metal did you use? I might have just missed.
Eutectic gallium indium.
Gallium indium. Okay, so it's just the common eutectic we use. Oh, that's
the cheapest one.
Yeah. And Martin, you mentioned earlier that you actually hate the project at the beginning. Now I can see you're very passionate about it. So can you perhaps give some hints to lots of young researchers who are hating the project they're doing, and to tell them how to actually overcome this kind of difficulty at the beginning?
So for me, I was very frustrated because I started getting I was in a group and we were getting a lot of data subject of transport, and my data looked different than everybody else. And what is going on? How come? You get to a point where you start doubting yourself. I was a postdoc. I'm like, is my data really good? So then I start asking other people, hey, do you mind taking measurements on this molecule? We ran blind studies with undergraduate and other postdocs to see whether they'll get the same thing. And every time they measure it, we will get the same thing. And I said, oh my goodness, then this must be true. It's not me. But at that point, when you get different data, you feel like you're failing. You feel like, oh my God, this project is going to be horrible. Why did I even start it? Because you cannot see a clear end. You cannot see the paper coming together. Mm-hmm. And it took us about 2 years and quite a bit of people to really go through this and get the same data over and over, irrespective of experience, irrespective of their background. And that's when I started now becoming a little bit more confident that actually this data, we should try to explain it instead of running away from it. And I want to thank my friend, Chris Nyhouse, who was my mentor, senior postdoc colleague at the time, was encouraging me to move ahead. But I was so stuck on, I should be getting a straight line in my data feed. But I can't, right? So I'm like, I don't know. So that's when I started now digging in. And the more I dug into the project, the more I realized, wait a minute, this is actually something very fascinating. Because we're sensitive to a single carbon. And if you think about it, a single carbon, and all you're doing is touch it with a liquid metal, how can I see an event that is happening at 0.1 nanometer? How is that even possible? And of course, as good scientists, you question yourself. You beat yourself up. You look into statistics. The data is statistically valid. But then, is your explanation right? And I think for a lot of young people, when you hit that wall, you feel like the data is not looking at like what is expected, especially if you're in a field where people who are very famous are published. My mentor, George White, is the one who published the paper in 91. And I'm in his lab and I'm getting something that is against what he said in 1991. What am I supposed to go tell him? You shrink, you feel very small. But for those young scientists out there, when you feel that way, I would encourage you to actually go back to data, because data never lies. Data, if you collect good data, it will tell you exactly what is going on. If you make a mistake, data will tell you you're making a mistake. And so after we saw this over and over, in 2011, we published a paper. And since then, I found something to work on, and it's really a project I like, because it fundamentally is so simple, so simple, that all you need to do is make a monolayer, put a drop of water, and you can start understanding what is happening at 0.1 nanometer. It's amazing. It's mind-boggling.
That's great, Martin. So you've now showing that you have using this the very nice, simple way of, understanding sub-nanometer structures. That's applied, of course, when your sort of sample system. Have you actually applied to other system, and then trying to see how, universal HD is basically, and also the other interesting, perhaps, molecular structure that could be directly linked to, applications. Have you looked at those systems?
That's where we are going. We have ventured into first understanding all the fundamental forces. This is a very fundamental project. We want to reveal the basics of the interaction before we can even claim we can make anything. It is not until that last paper I showed you, where we are inverting conductivity by changing the carbon, that is our first step towards now starting making functional electronics. So we do have actually some work going on in the lab by my postdoc Julia, where we are tapping into that interaction. I have a student and a postdoc working on this, and we're tapping into that actually to get into the semiconductor industry. And once you start applying that to semiconductor material, oh my, it's way fascinating. It is way much better than what I shared today. So I can't wait to start sharing this at another forum or some other time, because now not only can you use that interaction to force metals to be organized, or to force molecules to be organized, like Professor Thuo was asking, you can actually induce helicity. You can actually force the assembled system to form coils, like I was showing in the molecular machine. That coiling has a huge repercussion in the dimensionality of the nanomaterial you build, because we can use that coiling to control aspect ratio of one nanomaterial, nanoassembly. We can actually now start saying, at this point, I want to organize these type of oxides or semiconductors, and at this point, I want to continue the growth using a completely different material, and therefore change the twisting, change the interaction, and create internal strains and change the properties of that material at the same time. So the application is limitless. If you take those simple interactions in whichever field you're working in and pay attention to them, split them to non-polar interaction, polar interactions, and realize that with these interactions, some of them are directional, you can actually force things to organize in exactly the way you want. And you start making very interesting new materials.
That's excellent. Yeah, thank you for that. I think we're running out of time, but I might have one quick question. Chao, do you have any further questions, Martin?
So actually, I see in your slides there are a lot of some equations. So in your experiment, because actually it's in your research, you may get some experimental results that data may not fit your equations very well. So how do you handle this problem in your research? So can you explain to our young scientists?
I always tell a student, every equation you're trying to use, write it down and find one model that was before that, and write down all the assumptions that were involved in developing the models. Never, ever take any model and shoot it straight into your data without understanding what are the assumptions, what are the boundaries, what are the working limits of the equation. And the equation I showed you actually are all derived from the pre-equation. right? It's a really, really simple wetting force equilibration equation. Actually, you can derive it all the way from Newton's equation of motion, right? And then you can actually, I make my student do it. We have to go through all this. Derive from the most basic and then start every step of the derivation, apply your system. Ask yourself, when you say force equals mass times acceleration, what does that mean in your equation? What does that mean?
The potential influence factor is not fully included in your model. So how do you make sure that? Because there are several potential influential factors, but your equation is simpler than the actual system. So how do you guarantee?
So then you borrow from different fields. Like one of the equations I showed actually is a fusion of various fields. So you take, okay, if I want to understand work of addition, it's derived from force balance. If I want to understand dynamics, molecular dynamics, that's Boston, that's Brownian motion, that's a different equation. You have to synthesize them and bring them together. Because if I use one or the other, it doesn't make any sense. Yes. So it's you to look for similar points. In every model, you can look at overlapping points if they're addressing the same system. And once you find that, you link them together. Right? And then always, I start with the assumption that everything is additive. If I make an additive fusion of the equations and it doesn't work, then I say, then there are forces here that are interacting with each other. Maybe I start need to looking at a dot product, cross product, or something like that. Right? So it's a simple try and error, but you have to always go through the first principle. Don't expect to get an equation that always works. That's my mantra. Take the simplest of those equations and try to apply them to your work, and then build the complexity. Let the complexity come to you. Don't go looking for it.
Okay, thank you very much. A nice conclusion here, and that's probably what we have all the time for tonight. So now, thank you, Martin, for a fantastic talk and also the discussion. And now, I think it's the time for me to present ICANX Talks to actually give you this certificate. It's always your job before doing that, but I'm really pleased to give you that one. I'm sure Alice will deliver to you by email very soon. Thank you for your contribution. That's great. So next Tuesday, our again young scientist ICANX Talks for we have special young scientist awardees to present their talk. So please do tune in to join us. I guess that's all for tonight, and thank you very much for everyone attending the talks today. Bye, everyone.
Thank you.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。 奇迹。我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。I can，没有什么可以阻挡心